All right, thanks. So yeah, my name is Chris Smith, for those of you who do not know me. By day, I am a software engineer at Google, where I work on Google Classroom, our like education product for teachers to post homework, things like that. That's not what I'm here to talk to you about. So I'm here to talk to you about something I've been doing for about 8 years now in my spare time outside of work, and that is, teaching functional programming, and specifically a variant of the Haskell programming language, to children starting at age about as young as 10 up through about 14. So I'll tell you sort of why I would do such a thing, and then I'll also tell you kind of about the context in which I'm doing it, what I'm doing, and what problems that I'm hoping to solve by doing this. So first of all, what is the context? Well, schools care about some things, right? And one of the things that schools care about is algebra and teaching math. In fact, schools care quite a bit about this. So this is Sandra Wilder, among many other educators who are saying the same thing, saying that algebra is a gateway to STEM, and STEM is education jargon for science, technology, engineering, and mathematics. So basically, if you don't know algebra, you're not going to learn physics, you're not going to learn biology, you're not going to certainly learn advanced mathematics, and so on. But the truth is that many students don't learn algebra very well. In fact, I don't know if any of you have taught like university level calculus, but if you have, you find that actually a lot of students don't struggle so much with like applying the chain rule as they do with simplifying the algebra expressions they get back afterwards, right? And so there's a really interesting bit of research book I read recently called "And the Rest is Just Algebra," a collection by Sedeva Stewart, who basically makes this case that like, okay, we're so focused on how to teach our content that we don't realize that our students come into the rooms not even knowing the basic algebra to put the answers into context once they're done. So schools are doing a lot about algebra. One is they're trying to push exposure to algebra concepts to earlier and earlier ages, and by earlier I mean kindergarten in some cases. So kindergartners are doing exercises where it's like 3 plus blue equals 5, what's blue, right? And then the other thing that schools are doing is trying to focus on struggling students. So those students who are sort of not really quite getting it in their on grade level mathematics classes, it's fairly common these days to see them suddenly find themselves scheduled for a second math class, an enrichment or support math class, as well as their on grade level mathematics class, because schools are noticing that succeeding in algebra is really important. But I don't think we've quite cracked that nut yet. So that's part one of the context. Part two of the context is everybody wants to teach computer programming. So we're here in New York. A few years ago, the mayor of New York was Michael Bloomberg, and he made a lot of news by announcing that he was going to learn to code. So why does the mayor of New York need to write code? Well, it was really more to encourage everyone to learn to code, because coding is the way of the future. Well, there's a bunch of reasons why people are interested in this, and some of them good, some of them bad. But one of them is, well, we think everybody should be a computer programmer because that's a good paying job. That's maybe not my favorite reason. Another reason is we want some people who may not have seen themselves as being capable of being a computer programmer to at least have the opportunity to consider that line of work. But the third and the most compelling, I think, is really that there are some ideas that computers have made accessible now that are really universal ideas, that just for the purposes of understanding the world around us, of living in this world, it's a good idea to learn these ideas. So this idea goes by the name computational thinking, and I think there's a lot of debate over what exactly fits into computational thinking, what really is a universal skill coming from computer science, but I think it boils down to 4 things, right? First is understanding the structure of information. Second is breaking down complex problems through hierarchical decomposition. Third is reasoning with abstractions, and fourth is experimenting by using computational modeling. So these are not new ideas related to computers. Now, we've famously been told that, computer science is not about computers, by Dijkstra, by Hal Abelson, by a bunch of people. It's not about computers at all. And this computational thinking ideas are things that people have been doing for 1,000 years, but they were previously a much smaller part of the experience of performing tasks. So when you want to build a bridge, you need one person to think about the abstract ideas, and you need 100 people to pour cement, right? When you want to build a complex system using software, you need one person to think about the abstract ideas, and then you're done. So that's an interesting thing that computers do to the world. And education has an opportunity because computation is available in education and can make higher order, more abstract thinking more immediate and accessible to more people. So that's really the thing that motivates me here. Not so much that I want to make more computer programmers or software engineers as that I want to make ideas more accessible and make abstract thinking more accessible. So that's part 2 of my context. But we run into a problem, and that is it's not so much we should do algebra and we should do coding, but hey, wait, we should do art? Yeah, art's good. People should learn a musical instrument. They should learn history, because then if we don't learn history, then we repeat it, something like that. Hey, what else should we do? Oh yeah, literacy. Literacy is important. We should learn to read. Physical education, that's important. If you don't get physical education, then actually we see there are academic disadvantages literally to not getting enough exercise. Play is important for our mental health. Sleep is important. But wait a second, there's only 24 hours in a day, right? And so as algebra is now saying, wait, we want 2 of those class periods in school, not just the basic class, but the enrichment class. We're saying, let's add a whole new topic here. So I didn't mention this quite so clearly, but here we've got Mark Sermon, and he's not the only person saying this either, but he's describing code as a 4th literacy. In other words, he's saying education should be about reading, writing, arithmetic, and coding, right? I think that's going a little far, but the fact that that viewpoint is even in the conversation is shocking to me. So now they're saying, okay, we're adding this 4th literacy. We have all the stuff that's important. Wait, how many hours are in a school day again? So actually schools don't measure instruction in hours. They talk about instructional minutes. So every minute is something that counts. So at this point, we really have to choose our priorities. We can't really go have computer science go off this way, have math go off this way, and give them all the time that they want. So here's an interesting idea. Here's a teacher in front of a class. They're going through some vocabulary for today's lesson: function, variable, expression. They've got an example, y equals x plus 4. So show of hands, how many people think this is a math class? How many people think this is a computer science class? Yeah, so the point is it could be either one. Like, there's nothing on this board that is not somehow both mathematics and computer science. So one interesting idea is, are these even different? Is learning mathematics and learning computer science even a really different thing at all? Or are we actually talking about the same thing? And the answer is, well, sometimes they're different, right? Like, you're not going to, in school mathematics, study, computer graphics algorithms or machine learning or something like that. But in many cases, what we hope to find is that there's some sort of a core or essence of these fields that's the same. So remember, I don't care about teaching people, agile programming methodologies or anything like that. I care about, like, what's the underlying essential ideas that give you a better perspective or a better worldview. So what are the things that everyone should be learning? And I think they might be the same. So there's one problem, though, and that problem is our choice of programming languages. So most of the world still believes that we should program with imperative languages. And while imperative languages and mathematics both talk about variables, they mean very different things, right? The Java programmers mean a box. I stick something in the box, then I take it out, then I put something else. As I'm evaluating an expression, the values of the variables in that expression are changing. That's crazy, right? The second thing is functions. So functions to a mathematician mean a relationship between inputs and outputs. It's not a thing you do. You don't do a function. A function just relates one quantity to another quantity, right? In imperative programming, though, a function is like, do this, then do this, then do this. Now go back to step 5. It's a recipe. These are different ideas. They're related ideas. You can compute a function with a procedure, but they're not the same thing. And the equal sign means something different. So it's sort of become almost trite now to point out that if you're a basic programmer, you're used to writing x equals x plus 1, which is, of course, a lie. It's not true, right? X is never equal to x plus 1. But of course, the equal sign means something completely different. All of these, though, are just examples of the fact that in mathematics, we really we want to reason equationally and denotationally, and our tool of choice is substitution. If two things mean the same thing, I should be able to substitute one for the other. In imperative programming, none of those are in our toolbox. We reason with ordered effects and state, and if anything, we reason very indirectly about the semantics of what we're doing, right? It's not that we express the semantics directly in that language. It's maybe, if we're lucky, we have some indirect semantic reasoning about what's going on in the underlying, not very compositional underlying system. So that's the problem. The problem is not computer science and mathematics being fundamentally different. I think it's our choice of language. Okay? So, so I want to solve that problem. And my attempt to solve that problem, I eventually named CodeWorld. So CodeWorld is essentially my system for doing mathematics through computer science at K-12 ages, and specifically, I think about middle school ages, 6th, 7th, 8th grade. So pre-algebra, but not too much pre-algebra. So here's my story. I built this program initially. I mean, I've been doing education stuff off and on for, I don't know, 20 years almost. But not 20 years, no. Oh, yeah, about 20 years. But I started this computer science stuff maybe 2011. And I bought a house in 2003, actually, so a long time before this, and I moved in next door to this person named Sue Spengler. And Sue Spengler was a public school teacher. She taught history at a local middle school. And in 2010, 7 years later, she got so fed up with her job that she resigned, and she announced, I am starting my own school, and I'm doing it in my living room. And so right next door to me, I had this school. It had, a handful of students. I think it was 6 or 8 or something like that. So she found these students. She got them to come over to her house every day. She would teach them all day long. She said her job title was head teacher, principal, librarian, custodian, and lunch lady. And so that was just what she did, and it was great. But she came over to me and she said, hey, I know how to get people excited about history. I know how to get people excited about writing. How do I get people excited about mathematics? So my first answer was recreational mathematics. It's great. Martin Gardner's stuff, you get to do puzzles, solve games, and I did that for a year, right? We solved the Towers of Hanoi, we solved the art gallery problem, we made up gambling games where the kids had to write a report proving that the house had an advantage in their game, and then we made a casino with Monopoly money and invited their parents to come gamble. So we did all kinds of cool stuff. But at the end of that year, I looked back and I said, okay, let me think back over what I was doing. And the one thing that stuck out was that I would come over and they would sit and wait for me to tell them something interesting today. And I wasn't happy with that, because eventually, if you want someone to really take off on their own, you can't just train them to sit there and wait for someone to give them something interesting to do and tell them to do it. So I started to think, how can I come up with something which is still mathematics, still getting people excited about mathematics, but is about doing something on their own, about building things that they want, about communicating and expressing things of their own creation. And so this is when I came up with CodeWorld. I said, hey, look, I know this programming language, Haskell, and Haskell is great because it feels very mathematical, right? It feels like doing math. How you agree with this, right? Writing Haskell feels like doing math. Sort of? Okay. I mean, I feel like I'm qualified to say this. I actually have published math research in abstract algebra, and I've written Haskell, and I feel like they're similar, right? And so then I showed up, and I was like, all right, Haskell, 7th graders, it's going to be great. And it was great, but it was great in a slightly different sense than I thought it was going to be. It was great in the sense that Sue Spengler, who you see in the top left picture here, was awesome in that she was able to manage all the stuff that I did not know how to worry about, like the attitudes of the students and their experience, their frustrations with how they were learning, things like that, which I had no clue about because I was just going in there. I was like, I'm so excited about what I'm teaching, and I didn't pay attention as much as I should have to the kids that were in the class and what their experience was. So after I really went back and recapped that, then I said, okay, I can't just go in and teach Haskell. So I started to modify Haskell into something that I could reasonably teach at a middle school level without the Herculean efforts of a Sue Spengler in the room. And this is what I've been doing since then. So Haskell is a great language in the sense that it is a research language, and because it's a research language, there's lots of customizability in GHC. So I'm able to build something that doesn't even look a whole lot like Haskell, and yet it's still Haskell, well, sort of. So since that, you see a picture of Brooklyn Cook in the bottom left there, teaching at a school in Mountain View. She taught an all-girls class there for a school year. That was great. I assisted with that class. These are my students at Parkside Parkside Middle School in San Bruno, California. I've been teaching in New York this school year. So I've been doing this in a lot of places, like 5 different states. I think between myself and Fernando Alegre at LSU, who's been doing this with 9th graders, I think we've reached maybe close to 1,000 students by now. So here's what I do. First of all, I built this web UI. So I basically just stuck a code editor in a web browser, and you write some code, and then Lauta built this awesome thing called GHC.js that compiles Haskell to JavaScript. And so you compile to JavaScript, you run it right there in the browser. So you can build like nifty little graphical programs. You can run them right there in the web browser. So that's pretty awesome. It's a lot of work because I'm essentially reinventing an IDE, but from the perspective of children. But I won't get into the details of how I've customized the environment. I really want to tell you like what the core of what I'm doing is, and that is I'm starting with pictures as first-class values. So we start with some primitive pictures, some circles, some rectangles, some polygons. We start with some transformations that operate on those pictures. So translated is a function that takes a picture and a couple of numbers and gives you a new picture, which looks just like the first one, but it's offset a little bit in the X or Y direction. Rotated, dilated, or scaled. So all of these are actually words, incidentally, directly from the middle school mathematics curriculum. They study dilation, rotation, translation. They just don't study it for the purpose of doing art. They study it for the purpose of answering questions about congruence and similarity of triangles. And then also coloring. Coloring is an important transformation that they don't study in middle school mathematics, but it's an important way of changing a picture, especially if you want to be creative. And then second, you need to be able to compose multiple pictures together into more complex pictures. So we have this operator called ampersand, and ampersand is the in front of operator. So you have this picture in front of that picture. All these pictures have transparency built in, so you can layer one in front of the other and build up complex shapes, and students do so. So here's some examples of some of the complex shapes that students build up by starting with these geometry primitives, applying transformations to them, and then layering them on top of each other. So we have the haunted house was 1 month into a class. I had this student who, it was like Halloween time, and she just really went crazy, decided to make this haunted house. They start with pictures like this, then they move on to animations. So what's an animation? It's just a function from time to picture, right? So you already have all the combinators to build a picture, now you just write a lambda, or a function with a name actually is more likely the case, and you can build an animation. And then finally they get into, like in this bottom right and bottom left corners, you have games. So what's a game? Well, a game is, it's a little more complicated, but it's not too complicated. It's an initial state. It's a function from state and event that happens to a new state, and it's a function from state to a picture. And that's it. That's a game. So this event type has a couple of different options. It has like mouse clicked, mouse released, key pressed, time passed, which gives you a DT value, which is how much time passed since the last time a time passed event showed up, and so on. So all these things trigger changes in the state. And then they make stuff. So that's pretty cool. And we have a good time. So kind of real briefly, because I'm running out of time and going slower than I should, what do I actually teach? Well, so I start out by just teaching how to compose expressions. That's my number one topic, is like, how do I take variables, how do I take basic built-in primitives and compose them into expressions? How do you even understand an expression and a sub-expression? Do you know that a sub-expression has a value of its own, and that the operations between sub-expressions that compose these bigger expressions are just well-defined simple functions on the values of their sub-expressions? Like, these are ideas that we take for granted, I think, but as a 6th grader, these are kind of new to you, right? nested recursive expression structure is a new idea. Right? And so we also talk about top-down design in the same context. So how do I build a complicated picture by breaking it down into slightly less complicated pictures, and each of those into smaller pictures, and so on. Then we talk about, in our second unit, we talk about recognizing repeating patterns and building functions with arguments. So that's another big step because they're doing abstraction for the first time. So actually we have to hit this pretty hard. It's not an easy thing for them to learn. We have to go through a whole bunch of examples of like, hey, wait, let's talk about this. Let's write out like, what does a red ghost look like? What does a blue ghost look like? What does a purple ghost look like? Okay, let's find the common pieces. Let's find the pieces that differ. Sometimes you have to rewrite the expression a little bit so that these expressions you wrote separately actually do have a common form, and you can pull out the pieces that are in common, etc. So that's a bit of work. Then we get into animation and continuous change, and animation is of course just a function from time to picture, so you get like a bunch of different frames, each of which is a picture. So now we're talking about functions on numbers. So up to this point, their functions have all been functions that build pictures. Now they're talking about actually like different built-in functions on numbers. What's a quadratic function? What's a linear function? What's a sine wave? Things like that. What's a piecewise function? Then we get into combinatorics and repetition, and here we're actually doing like list comprehensions. Actually, is the language tool we're using for this. But we're talking about like how to like if there are 3 possibilities for X and 4 possibilities for Y, how many shapes are we going to get? Where are they going to show up on the screen? How do you understand that stuff? And then we get into state. And then we get into structured data. If I want a bunch of enemies, I need a list of enemies, but each enemy is a tuple with an X and a Y position and a health or something like that. We get into computation, where we start building simple, very, very simple, like actual recursive computations, list processing functions, things like that. And then eventually we get into modeling, where we start actually using these tools to do like model actual behaviors. Okay, so that's basically what I teach. That's the ideal case. So another thing that I did was I started focusing on motivation. So this first class that I taught with Sue Spengler there was great, but all because of Sue Spengler. And when I sat down and tried to write out what I was doing, it turned out that it was dreadfully boring. And so then I started looking for ways to make it less boring. So I paid a comic artist to write a comic book about some middle school kids who find a robot, and the robot speaks only in GHC error messages. And then I made sure that you could be social. You can share your programs with other students using just a URL. You can create galleries of your projects, things like that. But finally, just to wrap it up, I want to answer 2 questions. First of all, how is algebra good for computer science? And this is a picture of the Tower of Babel, the story that says like people were cursed by being forced to speak all different languages like Racket and Scratch and Python and Logo and Java. I think like this was a very prescient story. So the idea is, we could teach computer science by trying to pick a language. I've in fact talked to middle school teachers who are like, hey, I want to do an overview of computer science for my students, so I'm going to do a week of Python, then a week of Arduino, then a week of Scratch. It's like, no, learning more syntax is not the goal, right? So, but they already have to learn algebra. So if algebra were just a programming language, then problem solved, right? And then the second question is, how is computer science good for algebra? And math has kind of a PR problem, right? So if we want kids to learn to read, so we have a $4 billion industry producing children's books that they want to read. We want them to learn science, so we research dinosaurs. Scientists don't care about dinosaurs that much, except that kids care about dinosaurs, right? And we want people to learn history, so we have ninjas and pirates and cowboys and stories about them, and we captivate kids' imagination. And then we want them to learn mathematics, so we tell them that they can use it to get a better deal on bulk laundry detergent. So what I want to tell them is this answer instead, which is mathematics is a language you can use to express yourself, to be creative, to communicate your ideas, build stuff you care about. And that's basically my goal. So thank you. I'm happy to answer any questions in the 3 minutes.